Okay. So now I'd like to request Dr. Norman Margolus. Norm, can you please share your insights and views on Morita's work and your work similarities? Over to you, please.
Wait a second. Kamalaka, thank you for inviting me to give a talk in your memorial seminar. I need to start by apologizing that I never knew Kenichi Morita, despite the fact that we worked on similar things. I worked on stuff, I guess, a bit, my CA work, or my main CA work was a bit earlier and more physics oriented. So I attended lattice gas conferences and, meetings on quantum computation and things like that. I was, eventually vaguely aware of his work, but, I wasn't so interested in proofs of computation universality because there were other properties that I was very interested in. But, seeing the presentations and, the comments by people, he was obviously a brilliant and very kind man. And, now that I've looked at some of his work in more detail, it's unfortunate I can't now talk to him, but I'll talk to you guys instead, I guess, because he's still around in you guys. So I'm going to try to talk about, you asked me to talk about the impact of Morita's reversible cellular automata work because it was similar to some things I've worked on. I don't know that much about the world and, what the real impact is, but I can tell you what I think is very interesting about his work and what I think matters. So to give some context, and this goes back to what Katsunobu was saying yesterday in his talk. Digital information shows up at all sorts of scales, in computers, in our brains, if we're thinking about arithmetic or, things very digital, in the replication process of, DNA in our biology. These ones are sort of thermodynamic. So things like momentum don't really matter, but energy and, efficient use of energy and being able to do something at all. The DNA mechanism is extremely baroque. It has extraordinarily complicated pieces of machinery, to like make strands cross and all of that. But it does it somehow. And, the drive for people to find computation universality in cellular automata with constructions that take 23 million or 24 million steps to explode the bomb. I think that's part of the same tradition that evolution had, finding some way to make, something that could exactly digitally copy something, because, that's the characteristic of why information shows up at so many scales, is because if you find the digital information can be copied exactly, and therefore, you control, like evolution controls how many mistakes it makes in order to try things and so on. Analog information, you don't have that kind of control. In physics, these are all supposed to be physics. Things like momentum and macroscopic behavior are very important. Information shows up from the largest scale. This is a picture that people took a while ago of a black hole. And information, black hole, the maximum information you can have that's proportional to the event size of the event horizon in a black hole. Somehow, digital information shows up there. Quantum mechanics at the opposite scale, is really the source of digital information, because you have these perfect, exactly identical things, which are like bits in the world. And in between, we have like classical mechanics. And so my tradition, the area that I'm coming from, and the things that I care about are sort of this bottom set of things. And I think Morita was more concerned with these, but there's certainly overlap, because if you think about the details of what's possible, you need to work from both ends, I guess, in order to really understand something. So that's the context, I would say that my own interest in this stuff, which informs my viewpoint, like I'm sure a lot of other people, came first as a kid from seeing the Game of Life. And in the Game of Life, you know, if you like computers and you like physics and you see the Game of Life, you see that somehow we have a world here, at least a microscopic world, and it does stuff. And at least my immediate reaction was, oh, look, you can have a computer world, right? I wonder if our world is like that. And, you know, I think perhaps a lot of people are interested in cellular automata started off that way. Here's just a random pattern. And this is running, I think, at a few hundred frames per second, actually. And, well, that's interesting. Anyway, the thing dies out, at least macroscopically, in just a few thousand steps. But if you look close, you can see there's a little bit of stuff still going on. But this has to do mainly with one particularly physical property, which the Game of Life doesn't have, and which is one of the reasons, at least from a physics perspective, and also from other perspectives, you know, why reversible systems are interesting is they don't die out. They can't do this, right? Because they have to be able to go backwards. And how do you go backwards from this, right? And this is also very interesting from the point of view of people who sort of think about thermodynamic computation, you know, biology, DNA, all, you know, chemistry, all that sort of stuff. Because the fact you can't erase information in physics is what gives entropy so much predictive power. And I, you know, if you don't understand it, I'm not going to explain it right now unless you have asked me to, because I want to just talk about cellular automata. The other big event that sort of changed my viewpoint on all this stuff was Fredkin's billiard ball model. Because I thought that, you know, there's some connection between physics and computation. I know that information is digital in quantum mechanics. Essentially, it's finite anyway and discrete. But how do you get from classical models of computation all the way to quantum mechanics? And this model kind of bridges the gap between the continuous and the discrete. Here, I'll go backwards. Well, that's not looking quite right. Anyway, it's supposed to look like this, that the balls come together, okay, and they're on their paths coming in, but they collide and they're deflected outward. So they come on the outward path if there's two balls, which is A and B, and if only one ball comes in at a time, it's not going to be deflected. You'll get logic, A and not B. And that's, you know, somehow starting balls off in a very controlled manner on a lattice at controlled speeds, so all the collisions happen on the lattice and so on. You can make a model of computation, which is also a classical mechanical system. And so this is a bridge between physics and computation. You have energy in this model. What is the need for energy in computation? It turns out that you need energy to speed up computation. More balls mean you can have parallelism, essentially. But you know that there's no other need. But you also have the constraint in a model like this. Momentum is conserved. That means you have to deal not only with reversibility and energy conservation, but momentum conservation when you make a computation in the billiard ball model. If you don't care about momentum conservation, like in these biological computations, then you won't worry about that. And so there's some things I would worry about that Kenichi wouldn't have worried about. One of my first projects, when I started working with Fredkin was he wanted me to make a cellular automaton version of the billiard ball model. Okay, seems like a cellular automaton already, but there's a problem, which is that is my pointer on top of the line here or somewhere else? I can't, on my screen, I got 2 pointers somehow. All right, anyway, I won't worry about it. The problem is that you see this sharp corner here. A very local physical rule can't have a sharp corner like this for things that are just spatially separated. Somehow or other, you need some signal to go from here to here to make this guy bend and vice versa. And so making a very local cellular automaton that acts like this is hard. And well, it's impossible. And if you make it non-local, so it has a big neighborhood, then you have some complicated thing, and that doesn't seem very fundamental. The best I could come up with at the time was to cheat. Because the normal cellular automaton format was, many to one. But it seems obvious in a parallel system that you better not change stuff around you when you are trying to have some reversibility locally, because then when you want to go backwards, you won't have all the information you need to go backwards. So dividing the information up, in this case, into little 2x2 blocks, and only updating each one independently is one simple way to make sure that you always have the same information after you do something as before, but then you have to sort of make some overlapping blocks with another step, otherwise they're just independent blocks. So that's sort of the logic behind partitioning. And this particular rule is a block with one guy in it goes to the one goes to the opposite corner, and 2 flip, and the rotations of that also, and nothing else. All the other cases don't change, and that's reversible. And if you run this, this is a circuit kind of things that Kenichi made, but we did a lot of that too. At least to show the thing's universal. In this case, it's actually implementing a couple of Fredkin gates hooked up in a way that makes a complicated permutation sequence, a random number generator. And the reason you have pairs of balls here, it can actually be any spacing you like, because the whole thing is scalable, is they represent the diameter of a ball. And when they collide, the front part gets stuck and goes backwards and collides with the other part, which then does it again, and it gives you the finite spacing, but it also gives you a delay. And so this is this particular cellular automaton. It doesn't have this beautiful property that the original billiard ball model had, that it's exactly conserving the momentum and the center of mass, center of energy, motion. So you have to add little extra pieces to compensate for delays, which in a momentum conserving, in the billiard ball model, you don't have that problem. So it's kind of elegant because it's simple and it solves the reversibility problem and it's universal, but it doesn't really solve the physics adequately, to my mind. And I'll talk about how, I'll briefly mention how you do solve the problem properly. But let me talk about something that has to do with Kenichi now, okay? He had these square partition cellular automata, okay? And here's his rule that actually implements exactly the same isomorphic dynamics to the billiard ball model. And he had these white things are the cells, and you divide the cells up into 4 bits, okay? And then each cell, you make a rule that it actually looks at the neighbors, that of the, 1 bit of each of the neighbors, and then it's gonna put the result in the middle here. Okay, and this is like well, I'll talk about lattice gases in a minute, because this is reinventing the idea of lattice gases that Jarkko talked about, that each bit only goes to one place. That's a kind of partitioning. You do this everywhere, okay? So you end up with this kind of setup, where all the white cells, all the cells I've labeled with white, they get all of their information from the cyan cells, and all the cyan cells get all their information from the white cells. And so that actually produces what's called a checkerboard updating, that cyan data always lives in a checkerboard, and it moves to the other checkerboard, and then it moves back to the first checkerboard, and it never interacts with the white data. Okay, so this is a well-known phenomenon that you might see, for instance, in a genetic drift model, where each cell just randomly chooses one of its nearest neighbors, and that gives you a checkerboard updating also. And if you run that for a little bit, you can actually see there's only 4 colors here, but you see 2 different simulations overlaid on top of each other, because the even checkerboard and the odd checkerboard are not interacting, and you can actually see the checkerboard. It gives you nice colors because you have all this dithering, right? But it turns out that and this is something I realized yesterday when I took a look at Morita's construction, that the square partition cellular automaton and the 2x2 block automata that I played with are actually isomorphic. They're the same. It's not just the billiard ball automaton, it's all of them. And I'm not sure if Morita realized that, because he mentions only the billiard ball one in his book as isomorphic. But in any case, it doesn't matter. This doesn't detract from all of the wonderful work he did on proving how you get universality in these different rules. Because I never did that. I only proved universality in 2 rules ever, and didn't do any of those sorts of constructions with this stuff. But here's how you show that there's an isomorphism, okay, in all cases. First of all, we turn the space, 45 degrees, okay, and then we'll just draw a partition, the yellow partition. So we have a black groups of 4 and yellow groups of 4, okay, and now assume that we only care about the cyan data. We're not going to simulate the white data at all. We just won't even bother storing it, okay? In this step, the new state of the white guy depends on these 4 corners, right? The data in these 4 corners, okay? And then after you update them, the white cells, where the white cells now have the cyan data, and it's these new white cells that are going to depend on the 4 corners. And this is the black partition. And so this is just exactly the 2x2 block partition that I played with. What he's done is he's simulated 2 independent sublattices. But my version just simulates one of them, but they're isomorphic otherwise, right? And so I think he was very happy to give a version which didn't have explicit time dependence. But I would say that it has implicit time dependence. And that's kind of just inherent in the idea of collisions, or, in physics, things collide. There's a little area that for a moment is where the collision's happening. Then things move away, and somewhere else, there's a little area where the collisions are happening. And so some sort of second ordinance or time dependence ends up being built in any case. He sort of combined a movement step and an interaction step in order to have a conventional cellular automaton. I would say, though, also that some of his constructions, like on the triangular lattice that he did with Katsunobu, this is a wonderful thing that has nothing to do with anything I ever did. And it's, as far as I can tell, the simplest universal 2D reversible cellular automaton anybody's come up with, because they do the partitioning on a triangular lattice, so there's only 3 bits that come in and interact. And he has this simple rule, with the rotational cases, and there's only one case where things don't just come in without changing, this case. And so it's really an extremely simple rule. And then he shows that it's computation universal, here again by constructing a Fredkin gate, and these black things are acting like wires. And this was in 2000. I know, maybe at the end, Katsunobu might have some comment on this, because I think was this something you did for your PhD thesis or part of your thesis work? Anyway, you can tell me later.
Yes.
And I'd like to also to thank Gennaro Martinez. I don't know if he's watching right now. He helped me find an example of a flip-flop, well, an example circuit that uses this, so I can actually show you something running. This is one of Kenichi's simulations. The other ones are extremely elaborate, and you have to zoom in, like all the way to see anything happening at all. But this one you can at least see. But it's quite complicated, I think, because he has to have like 5 different signals coming with the right timing to do the right thing somewhere. This involved a lot of patience to understand and make these things work. All right. Now, I was saying that these things are kind of closely related to lattice gases, because lattice gases is alternately move the data and then update whatever lands there. And that's the kind of partitioning that Kenichi does. And one of the reasons physicists like this is because you can make momentum conserving models. You imagine the particles are moving continuously in between the discrete steps, and you can see that physically that's a momentum conserving collision. And in fact, if you put a lot of particles in a gap in the middle, you get a nice sound pulse. And that's reversible also. So once you put the constraint of momentum conservation in, it starts to become a lot more physical. And there was a whole industry. Here's a 6-direction lattice gas with extra bits for obstacles and smoke and things. And you get hydrodynamics. And this was kind of the reason we ended up building all these cellular automata machines. It's because this looked useful. And that took a number of years of my life and didn't end up changing the world that much. But lattice glasses provide a way to solve the problem that I initially was assigned. This was in 2003. So 20 years after I was given the assignment to find a cellular automaton version of the billiard ball model, I solved the problem. This would have been a very long PhD program. And the way I found it was to cheat in a different way. Instead of having the balls hit each other and and have a hard collision at some finite different distance, they squash together, and that gives you the same kind of logic. See, they're about to hit. Here they squash together and come back out, and so they're displaced by on these they come out at a different place if they collide than if they didn't collide. And so again, we get exactly the same kind of reversible logic. But in this case, the centers of the balls did something very local. And this is a local interaction, and this is a local interaction. And so this is a cellular automaton. It's a lattice gas cellular automaton. Move stuff, interact, move stuff, interact. Okay? And I'm not going to talk about where I am today in all of this stuff. This is, I got us up to 2003, okay? But my whole program of research has been trying to see essentially how we get from simple classical local models to all the way up to something that's real, that's quantum mechanics and fundamental physics and so on. And eventually you can do that. You find out the classical mechanics is actually fundamentally discrete if you think of it as the most distinct possible limit of quantum mechanics. And you even find out what energy is, that you have intrinsic energy in your cellular automata models, which is basically just the least energy you could have to have this physical dynamics. So I have some papers that you could look at. There's one that I mentioned in my talk in the Fredkin Memorial, which is actually online now. It only took a few months more after I said it would be up there in a couple of weeks. What I can say, since this is a memorial, I could try to say something philosophical. But life is this long road, and you have to live it forward, but you only understand it backward, right? We figure something out. We're fumbling around, and then at the end we can tell a story that people can actually understand. But they don't see all the fumbling around, right? And that seems like an appropriate observation for a memorial about the importance of reversibility. But I thought that the most important point about the impact of Kenichi's work was the one that you guys made at the very end of yesterday's talk, yesterday's session, where you quoted a poem that undoubtedly the greatest impact that he will have is through his students, his colleagues, and his friends, by being such a smart and good person and having such an impact on your lives and your interests. And if you guys figure out good things about cellular automata as a result, that helps me too. So that's an impact on me. So thank you guys very much. And if you have any questions, I can talk more probably.
Thank you so much. Thank you, Noam. Thanks for preparing all this. I initially approached and you were thinking, but then you agreed and prepared all this. Thank you so much for that. Thanks a lot.
I'm just a coward about talking without any preparation.
It's amazing. It's amazing. So I hope there will be a lot of questions and comments. Maybe Professor Kari or Professor Imai wants to comment on anything.
Well, it is not so legit because I am not so. I discussed with Kenichi about the two-dimensional universal PCA 16 state very long ago, So I am not sure, but anyway, he said, of course, this two-dimensional 16-state reverse partitioned cell automaton universal case is based on Norman's Margolus neighborhood. So I am not sure, but he noticed quite a few things, and so he anyway constructed two models in the paper. The first one is quite symmetric. So the rule is both rotationally symmetric and reflectively symmetric. But the second model is a bit different. So maybe.
Well, but I mean, it's just very simple here that informationally you're only depending that because there's two partitions, that because there's two sublattices, your data is centered on two different places as it evolves, and that's exactly equivalent to the partitioning. So I think that in different formats it makes you think about different things, and as I said, I didn't analyze computation universality. There were only two rules that I was interested in: the computation universality. So certainly all of the work that he did in playing with these things and demonstrating computation universality is something that's never been done before, or had never been done before. I'm just saying this particular partitioning thing, and other related ones that you guys thought of, like the triangular one, that's nothing to do with this. But I think this particular one, all of the square partitioning cellular automata are isomorphic to 2x2 block automata. I mean, you can check it. It's possible I made some obvious mistake here, but it seems very simple. When Kamalaka asked me to discuss the relationship of what I've done to what he's done, I just sort of looked at it, and the relationship was very close, actually, at least as far as I can tell. And I'm not saying he's copied it or anything. I'm just saying that with an independent, things that look different and can end up being the same. And the partition. I should also say that the triangular partitioning, in its own way, is not. I don't know exactly what rules you make for deciding what is a cellular automaton, because my one was explicitly time dependent, so that failed. But the one with the triangular partition, a triangle pointing up has two neighbors above it. A triangular pointing down has two neighbors below it. And so the neighborhood, if you think about the triangles as being the cells, the neighborhood is not the same for all the cells, right? So I don't know if that breaks any rules about cellular automata. It seems fine to me. Any crystallographic thing I'm happy with. But would you consider that a normal cellular automaton? I don't know what the rules are, what your definition is. Here, if we go back to this. You have, when a triangle is pointing up, two of the neighbors are above it. If the triangle were pointing down, two of the neighbors would be below it. If you have a single one over here, it comes into the cell. but it can't go straight because there's no side in this direction for it to go out. And so, in this particular model, for instance, you can't have a particle that just goes straight. There's no place for it to go straight, right? And so it has to go off to the side somehow. And so, it's a different set of constraints.
Yes. So at the moment when I try to reduce the state number,
yeah, this is brilliant, by the way. Congratulations on this. I like it.
At the moment, at the time, we discussed with Kenichi, and he in the beginning he said it should be impossible, but but recently
that's good to hear. They always like it when you do the impossible.
But recently he tried to check the other combination of rules in the case of triangular cell automaton, and found even a triangular reversible partitioned cell automaton, you can employ gliders and their collisions.
You can do it.
So I have, at this moment, I have no idea of glider-like patterns can be employed and to be universal. I have no idea of, because of course the game of life is very impressive. So it is reasonable to think if you want to make an interesting cellular automaton rule, the cellular automaton should be include gliders and its collisions. But so at the moment, we have no idea of 8-state triangular case. It is possible to be universal employing the glider collisions.
Well, the thing I would say, go ahead.
But anyway, almost 10 years ago, Kenichi finally found a glider on this 8-state triangular cell automaton. So I was actually surprised.
Well, he mentions it in his book that it's some very large thing.
Yeah, very large. And anyway, he said he found the glider just because, in a sense, are happening. Just playing rules and random patterns. Try to place some configurations, and he happened to found the glider, and so I am not sure, but anyway, his many cellular automaton. Anyway, it is almost impossible to achieve with building a stack of theories. Anyway, just a simulation.
Well, I can make one comment about that. Is that at least from a physical standpoint, thinking about the world, if you want to have a cellular automaton, which is like an interesting world, you watch it and all sorts of interesting things happen. Computation universality is just the very minimum property you need to have an interesting world. Because, for instance, the game of life, I was showing from if you look at it, it's just gray, from far away. Nothing interesting ever happens spontaneously. It requires these very delicate initial states to do anything interesting at all. And if you really wanted an interesting world, you should have not only microscopic things that are universal, but you should have macroscopic objects that can move around and they can talk to each other and eat each other, and the property of having a cellular automaton that also has a macroscopic behavior, that there's large objects that do things, and you can maybe have universality in large objects also, but a robust universality. So you can have a world like ours, right? That's a whole different set of constraints, which are far beyond universality. But if you're trying to, if the point of a cellular automaton is to be a model of an interesting world and give you some idea of what it takes to have an interesting world, you need to try harder than just universality, I think.
Okay.
Now, almost everything's universal, right? Particularly if it's reversible.
Yeah. So we are sometimes extremely simple, even extremely simple. We just happen to found the system should be universal. So universality is quite a usual thing.
Well, particularly if you watch it run, and either it doesn't seem to do anything or it's doing stuff. And if it's doing stuff, usually you can find a way to make it universal, right? But if it's not something that happens, spontaneously, like just as entropy increases in your system, things spread out, you get something interesting, then it's not very robust. Here I can wonder if I have that's interesting. It doesn't let me. Oh, I know what I need to do. I can show you something from. I bet I have to stop my presentation in order to show you something else.
Sorry.
Okay. But you probably need to stop.
Yeah,
okay.
We are getting delayed. So.
Okay. Yeah, it's late there. All right. I won't show you. But this is something that in my when I gave the talk at the Fredkin talk, which by the way, Morita gave a talk there also, and I didn't see his talk, and I don't think he saw my talk. I don't know, because we didn't talk. But
yes, that was in different days. That's why you missed.
Oh, he was on a different day?
Yes.
Okay. Well, that was my best opportunity, probably my last opportunity. Anyway, thank you though for what happened to. That's
Thank
interesting.
you. Yes. Thank you, Norm. We'll come back again.